Welcome back. Today we're going to talk about exponential and logistic functions. To start off with exponential and logistic functions, we're going to look at exponential functions first. Exponential functions look like this. F of x is equal to a times b to the x power. So the x being in the power is the key to this, or it could look like this. A times e to the k x. Now, the thing that we're going to discover as we go throughout this chapter, not necessarily in this section, any of these functions, any of these initial functions, a times b to the x, can be written in this form. So can be okay, so any of these a times b to the x functions can be written into the form a times e to the kx. And a couple of the things that we need to know about it. A is the initial value. And we find that by doing f of 0. And b is called the base, of course, because we've got this exponent. Another note, if a is greater than 0 and k is greater than 0, f of x is a growth function. If a is greater than 0 and k is less than 0, f of x is a decay function. Okay, so growth versus decay. This is what we're looking at in this chapter is it exponential growth or is it exponential decay? Some examples of this, yes, would be 3 to the x or minus 2 times 1.5 to the x or e to the 2x. Some non-examples would be like 6x to the negative fourth or x to the 1/3 power. Okay, so x has to be in the exponent for us to have an exponential function. To evaluate these, it's fairly straightforward. If f of x is 2 to the x, f of 4 would be 2 to the 4th power, which would be 2 times 2 is 4, times 2 is 8, times 2 is 16. If f is negative 3, we'd have 2 to the negative 3rd power, which is equal to 1 over 2 to the 3rd, which is 1/8. If we've got f of a fraction, we could do 2 to the negative 3/2 power, which would be equal to 1 over 2 to the 3/2, which would be equal to 1 over the square root of 2 cubed, which is 1 over the square root of 8. And if I was going to write that as a decimal approximation, I'd have 0.3535, etc., etc. Okay? Exponential functions, I can evaluate them. I can also find a formula for them. Okay, so that first part was something you probably already know. We're going to determine formulas for the exponential functions f of x and g of x from these tables. Okay, so we've already been told that these are exponential functions, f of x and g of x. And so f of x takes this form, a times b to the x. Well, if we know something about the formula, what is a? What is b? Well, a, from up here, a is my initial value, or f of 0. So for f of x, what is f of 0? Well, if I look at my chart, here's 0. F of 0 would be 4. So far I have f of x is equal to 4 times b to the x. Well, I need to fill in a couple of these variables. I need an x and I need an f of x. Well, check it out. If I look here, here's an x, and this would be the f of that x. And so if I fill this in, 12 equals 4 times b to the 1st power. 12 equals 4b. So b is equal to 3. What does that mean for my formula? Well, if b is 3, I'd have f of x equals 4 times 3 to the x. That does not simplify to 12 to the x. It's 4 times 3 to the x. Let's do the same for g of x. Okay, so see if you can take g of x and figure out what the f of 0 is. Use one of the values with its accompanying x to figure out the formula. So pause here. When you come back, I'll have the answer for you. All right, so g of x is equal to a times b to the x. A is f of 0, so my f of 0 in this case is 8. And so I've got g of x is equal to 8 times b to the x. Well, I'm going to pick out a value here. I'm going to pick 1 and 2. So 1 equals 8 times b to the first. This should be 2. Sorry, that's my f of x. Started looking at that and it wasn't right. So my g of x, so that's 2, is equal to 8 times b to the first. That's my x. And so 2 equals 8 times b, divided by 8. So 1/4 equals b. So what have I got? I've got my f of 0. This is my a. I've got my 1/4. This is my b. When I put it all together, I've got g of x equals a, 8 times b to the x. 8 times 1/4 to the x. Well, really, where does this come from? If we look at the way that this goes down, if I multiply this by 1/4, 1/4 of 128 is 32. This would be 1/4. This would be times 1/4. This would be times 1/4. Okay, and so my decay, this is decay because it's going down, 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 down. My decay is based on this 1/4. Well, that's my b right here. See there? That base provides me with what's the factor by which it's decreasing. In this case, if I multiply this times 3, if I multiply this times 3, it doesn't become as obvious till here necessarily. Times 3. Well, look at this. This is a growth model. It's growing. My b here is making it grow as it goes up. Exponential growth and decay. Well, what does it look like? We've got some function here for any f of x equal to a times b to the x, so our standard exponential growth function. F of x plus 1, which means not f of x, but the term after that, so the next x, okay, is equal to b times f of x, okay? And if a greater than 0 and b is greater than 1, it's a growth function. Okay, that's what we saw up here. So my a is greater than 0. My b is greater than 1. So it was a growth function. On the other hand, if a is greater than 0 and b is not less than 1, but b is going to be between 0 and 1, like right here. See, b is between 0 and 1. 1/4 is between 0 and 1. Then it's a decay function. Okay, so we saw two examples of that right above here. So my growth function had a positive a b that was greater than 1. In this one, I had a positive a, obviously, and then a b that was between 0 and 1. Okay, so what do these growth models look like? Well, if I've got f of x is equal to b to the x, and this would be b is greater than 1. It's going to go through this point here, which is 0, 1. And it's also going to go through this point here of 1, comma, b. And it's going to go like this. Exponential growth, going up as x increases, y increases. My decay function is going to look like this. My f of x is equal to b to the x. Again, this exponential function. And my b is between 0 and 1. Well, this is going to go through 0, 1 also. And it's going to go through 1, comma, b. But look at this model. This is exponential decay. It's going down. Well, you're thinking to yourself, well, if it's 1 comma b, how could it be up here and then down here? Remember, b on this one was greater than 1. So this is like, for example, 1 comma 3. On this one, it would be 1 comma 1/2, 1 comma 1/8. And so it's going to be below this 0, 1 line. So growth goes up, growing. Decay goes down. Okay? When we transform these functions, then it's going to do the exact same thing that we've been talking about all along. So what I'm going to do is this. We're going to compare the graphs to f of x is equal to 2 to the x. So what I'm going to do is I'm going to draw in a coordinate plane here. All right, and if I've got 2 to the x, it's going to go through 0, 1, and it's also going to go through 1 comma 2 because that's my 1 comma b. And I'm going to have my original function that looks like this. Okay, sort of looks like that. The first one that I'm going to compare is, so A is f of x equals 2 to the x minus 1. Okay, so this is where it starts to get a little bit like, what did we do before? What do we do now? Okay, so if I've got 2 to the x minus 1, this is sort of like inside the function, right? So that would be like when we had, x squared versus x minus 1 squared inside the function. And so this one moved it right 1. Well, the same thing is going to be true here. So when I look at these functions and try to determine, well, where does it go? What happens? I'm comparing it to things that I've already looked at. And so this one's actually going to go from 1, 2 to 2, 2. This is going to go from 0, 1 to 1, 1. So it's going to flatten out because everything moved to the right 1. Okay? Second one. All right, my next one. I'm going to have f of x is equal to 2 to the minus x. Well, think about it in terms of our x squared example up here. It'd be the difference in, x squared versus negative x squared. So this is going to be reflection over y because it's negative x versus x, okay? And so if I get a reflection over y, I'm going to have this, and I'm going to have negative 1 comma 2. So it's going to go kind of like this. Testing my dot connection skills. Next one, C. 3 times 2 to the x. I'm taking my function, f of x. I'll just rewrite it. F of x is equal to 3 times 2 to the x. I'm taking my whole function and multiplying it by 3. Well, that was that vertical stretch mentality. So it would be like an x squared versus 3 times x squared. And so I take my point 1, 2, and it's going to be times 3. So it's 3 times my y value. So this will be at 1 comma 6. And it's going to go this way. Stretched way up there. It's not going to go below the x-axis though. Come this way. So not that part. So this point right here, it's also going to be 0, 3, because this one gets stretched by a factor of 3. This one gets stretched by a factor of 3. So everything gets stretched by a factor of 3, so it's going to go up more like that. And then as I drew here, doesn't go below the x-axis, but comes up and goes through those 2 points. So not this part right there. D. Trying to pick a color here, orange. Let's do one more. F of x is equal to 2 to the 2x power. This one's a little bit tricky. Okay, so we didn't necessarily deal a lot with this in the past. We've done it, but we haven't dealt with it a ton. If I've got 2x here, that would be like saying 2x squared. So it's on the inside. So really this is f of 2x. Well, when it's inside like this, it's not a vertical stretch, it's a horizontal shrink, right? And so what is it a horizontal shrink by? Well, I remember that this is like x over 2, f of x over 2 would be the same as f of x over 1/2, because that would make me have 2x. So f of x over 1/2 would be the same as f of 2x. And so it's a horizontal shrink by 1/2. Well, what does that look like when I actually shrink it? I take my point, 1, 2, and I move it in 1/2. So I'm going to put it right here, and it's 1, 1/2. This one doesn't shrink any because it's horizontal, so 0, half of 0 is 0. So it's still going to go through there, and it's going to look like this. Okay? And so I'm doing all this to say it's the same. The shifting is the same. If it's in the exponent, the x is in the exponent, if we're subtracting or adding to it, it's left and right. If it's a negative, it's going to flip it over. If there's a number out front of my base, so like a times b to the x, that a tells me my vertical stretch. If it's inside, so next to the x in the exponent, a 2 or a 1/4, whatever it happens to be, that's going to affect my horizontal shift or shrink, or horizontal shrink or stretch. Okay? Logistic functions. Last thing we're going to talk about is logistic functions, and with the logistic function we've studied this as one of our 12 basic functions that we looked at, and the thing we need to remember is this: a, b, c, and k are constants, and I'm going to show you the formula here in a minute, and b is less than 1. Our f of x for our logistic function looks like this: c over 1 plus a times b to the x, or c over 1 plus a times e to the negative kx. These are our two looks that we're kind of looking for our logistic functions. A couple of notes. If b is greater than 1 and k is less than 0, this is a logistic decay. If a is equal to c is equal to k, and all of those are equal to 1. So we have this situation where all of our, a, c, k, all 1. This is just the logistic function. And this is the one that we studied when we were looking at it in the 12 basic functions sections. So it would look like this: f of x is equal to 1 over 1 plus e to the negative x. A couple of notes on this. And we've already looked at this, but it's obviously going to be a refresher because it's been a while. The limit as x goes to negative infinity of f of x is going to be 0. So it's going to come down and approach 0 on this end, okay? And the limit as x goes to infinity of this f of x for this one is going to be c, or whatever's on top, in this case 1, and so as we go up, this is going to approach 1 as x goes to infinity. And so that's the basic gist of these decay functions. The number on top is going to be our limit as it goes out to infinity. How high can it go? That's limited growth. On the bottom, our limit's going to be 0. So this wants us to graph the function, find the y-intercept, and the horizontal asymptotes. And actually, we're not even going to graph. We're going to use the function to find these two pieces of information. Our y-intercept is actually going to be f of 0. So if I put in 0, eight divided by 1 plus 3 times 0.07 to the 0 is actually equal to 8 over 1 plus, and 0.7 to the 0 would be 1, so 3 times 1. And so this would actually be 2. So that's our y-intercept, is 0, 2. Our horizontal asymptotes, as discussed up here, as it goes to infinity, is going to be my c, my number on top. 8 is our limit. The limit as x goes to negative infinity is going to be 0. And so I could even just sketch the graph now. So if my intercept is 0, 2, and my limit this way goes to 0, my limit this way goes to 8, y equals 8. That is my graph of my function. Okay, that's the basics of logistics. Go ahead and try this next one, and we will talk about it in class tomorrow. All right, guys, thanks for watching, and we'll see you next time.